Hello, everyone, and welcome to this latest Asset Colloquium. We are here hosting Mr. Singh Arun from IBM Quantum, and we are very lucky and looking forward to the Quantum Safe Cryptography lecture which he gives. I'll give a very brief introduction to him first. Mr. Singh Jai is TFR alumni. He was working with our STCS here for 2 years in late 1990s, maybe, yes. He did his bachelor's from NIT Bhopal and then master's from VJTI Mumbai. And then, of course, went to US and did his MBA in North Carolina University. And he has now 25 years of experience in industries with various project management. And he is also an author of a book on cryptography for business, or something the title for that side. Currently, he's heading a division in IBM, a global head of IBM Quantum Safe product. He will here to talk about the same thing, so I will not go much details on that. Without further ado, I request Jai to please start.
Okay, thank you. Well, namaste, and good afternoon, good evening, or good morning to those who are watching live on YouTube. As Mr. Shah mentioned that I am the TIFR alumni, so I do have fond memories with this institute. This was my first workplace after my college degree. And that was my first thing. Or not only that, I found my better half, my life partner, also in this institute. She's sitting right there. So we work together here. So thank you. This is absolutely a great place for myself and my personal journey here. So what we would like to do today is talk about the quantum safe cryptography. So this is one of the topics that many people may not be familiar with what's going on in the quantum computing world and how advancement of quantum computing can also threaten what we have currently in our cybersecurity space. So I'll just walk through some of these things for us. But this one already talked by Mr. Shah, so I will not take much of the time here. But this is the topic that we will understand here, that why are we talking about quantum safe cryptography today? And what is quantum safe cryptography in a nutshell? And who should be really concerned and be focusing on this in general? And when do we really need to start implementing quantum safe cryptography in our systems, applications, and all the business that we have today? And then obviously, how do we get started? So these are the things that we should talk today. But let me get to the first why part. Before I get there, I'm part of the IBM Quantum business unit, which builds the quantum computers. And also, there are two sides of the mission that we have. I don't know how many of you have watched the Spider-Man movie. There's a great saying that great power comes with great responsibility. So while we bring the quantum computers, it's the important part that if we are building the quantum computers, they are creating new capabilities for us to solve the world's complex problems that we cannot solve today with classical computers that we have now. However, they can also create threats for us. So I think I'll discuss about those things. And so equally, we are responsible to how we make sure the world is quantum safe against the quantum threats. So that's the part. And I'm on the other side of the business, which is making the world quantum safe. So some of you, I'm just giving you a little bit of primer on not getting into the more of the quantum computing side of the details, but just to give you a little bit perspective of how we see the difference between classical computers that we use today versus on the quantum computers we have. Very simple at layman's term, we know the light switch, 0 and 1, on and off, right? But if you can imagine the dimmer switch that we have nowadays in our homes, you can have multiple different possibilities in between 0 and 1. Imagine that kind of phenomenon in the quantum computing. So while we can only have 2 states in a bit in classical computers, in quantum computers, we have multiple possibilities of these states that you can have in the quantum computer. What does it give you? It can give you a lot of permutation and combinations that we cannot do in classical computers today. So that's in general, at high level, what the quantum computers are. However, Quantum computers, we are not thinking that they will be able to solve everything that we do with classical computers, but there are few problems that we cannot solve today with classical computers can be solved by quantum computers. Examples of them, many are in the, you can say, pharmaceutical research, physics, chemistry. Some of the typical examples, I would say, imagine that we would have a computer that can understand the molecular structure of insulin. If we were able to find the molecular structure details of an insulin, we would have developed the diabetes medicine 10 years ago or earlier than that. Classical computers cannot do that. It might be able to simulate the molecular structure that will take hundreds of years. And that's the difficult part. And we see that quantum computers can solve those kind of typical problems that we have today. There are a lot of other things like optimizations. We want to know in the financial services, there are things like financial frontiers, finding out the fraud detection, fraud prevention, those kind of the deeper analysis that we cannot do today with classical computers. Quantum computers can solve that. One of the other things besides it can do better machine learning, it can do better other things. One of the problems, it can also solve what we call factoring. Factoring is one of the biggest problems that we cannot solve today. And the reason it is important for our talk today, we should understand what do we mean by factoring here. Before I get there, I would like to ask many of you, how many of you do mobile banking from your phone or make the payments from your phone? Almost all of us, right? And second question I would ask that beside these things, maybe some of us have the ATM card and those things we use. I would say all of those things that we do in terms of credit card transaction, ATM card transactions, or mobile banking transactions, they depend on one of the secure connection between your phone and the banking server, right? Or application that's running. That's the mobile banking running on the bank side. It goes through a secure connection, and that security is built on an encryption. And that encryption technology we are talking about here today is I think that's why we say that modern world depends on the cryptography. Cryptography is the encryption schemes that are being used underlying, and that's how important it is. So you can see the transactions that we see, secure transactions throughout these devices across the globe. There are trillions of devices, billions of transactions that happen across all of these systems. And that's one of the things that we would like to understand, that this thing is at risk. And why I say that this thing is at risk is because this encryption technology that's being used today in our mobile banking, ATM transaction, or credit card transactions, they are based on this simple mathematical problem called prime factorization. So if I ask you what's the prime factor for 65, you will say 13 and 5, right? But there are this concept of public key, private key. So the concept of PKI, these are the two keys, 10248 bits, two keys combined together. That's 2048-bit number. That's 616-digit long number. I asked you the prime factors of 65, that's 2-digit number. You can say 13 and 5. But if it's a number 616-digit long number, finding the cryptography prime factors for that basically would be difficult for classical computers. And today's computer, if you ask them to find the prime factor of that 616-digit long number, it will take millions of years. That's why we say that we are safe. Our credit card transactions are safe. Our banking transactions are safe, because we think that's how the classical computers are today. But I would say they are not safe anymore, because quantum computers can find those prime factors in an hour. Peter Shor's theoretical algorithm has satisfied that the quantum computers of right caliber can crack the encryption techniques and can find those prime factors in an hour. So most of the things that we do securely in our digital world are at risk. So And most of the things that we should be worried about, not everything, but in general, the things that are, the concept of data at rest and data in transit. Data in transit, all the applications that we have today, like I gave you the examples of our mobile banking, where the data is coming from bank to your cell phone. So those are the data at transit. All the encryption techniques for data in transit are at risk. Data at rest should be fine for at least 10, 15 years, because there is another algorithm by Mr. Grover. Dr. Grover has said that if you can increase the encryption key length size, it can probably run 10 to 15 years more, and quantum computers cannot break until then. That's the part. But data in transit at risk, and this is also called asymmetric cryptography. So it's very, very important for us to be aware of that this is a threat coming soon, and we should be thinking about that, right? Okay, then you might be saying that what people can do if quantum computers come sometime later and they can crack our encryption, what can they do, right? First thing they can do even today, while quantum computers are not there, what they can do is they can steal the data from internet, what we call harvest now. They can keep stealing the data from internet. They cannot do anything today because they cannot decrypt it. But the time when quantum computers become available, they can decrypt that data and find the crown jewels from there. So imagine it's your $1 million transaction is going, who this guy sent this money to, or you may have seen that Apple iMessages have been stolen and celebrities' messages have been leaked out and things like that. So those are the kind of things that we would see that could happen later. But that's the part they are harvesting now. So this is at risk. This is a risk today that cyber criminals, bad actors can harvest that data now and probably decrypt that data later. So that's one thing. Once they are able to decrypt that data, what also they can do is fraudulent authentication, which is basically impersonating you as a person. Imagine you have locks in your home and keys. If a person is coming with the right keys, how would you stop him that, hey, you are not the owner of this house because you have the right keys? So the purpose of this is understanding when quantum computers are giving you, decrypting the data, can give you the right keys, the fraudulent authentications can happen. Also, there's a concept when we sign the digital contracts automatically in digital signing. So digital signatures are also at risk. So these are the things that we should understand that why they are at risk. Just to give you a little bit of what is quantum safe cryptography is, or it's also known as post-quantum cryptography, or also people call it quantum resilient, quantum resistant, different words, but it's the same thing. What it is, it's a new mathematical problem, and I'll explain what those are. So it's a new mathematical problem that cannot be solved by today's computers as well as quantum computers. So that's the new quantum safe cryptography. This thing does not require quantum computers. We are preparing and building this new mathematical problem for today's computers. So our today's computers are secure against the quantum computers threat. Just to give you a little bit more of details, what is quantum safe cryptography? Most of the new encryption algorithms that we have built for quantum safe are based on this lattice-based cryptography phenomenon. What is lattice-based cryptography? If you remember that we talked about the P and Q, or the prime factors, two values of prime factors. Imagine you have an XY axis and there's a curve, and I ask you a point on the curve and give me XY coordinates for that. You can easily tell what those are. The newer problem is based on multidimensional lattice, not two-dimensional, but multidimensional lattice, and there's a curve, and I ask you to find the coordinates of a point on that curve. It would be very difficult for classical computers to do that math problem. So lattice-based cryptography is the one way of having a new mathematical problems that even quantum computers cannot solve. Okay? So this is how we are building the quantum safe cryptography. A quiz question for you. Anyone knows that what was the first ever encryption technique that we have had, or computer encryption? I see. Okay. So I think the one of the first ever, I will give you the answer for that, is called DES. Have you ever heard the data encryption standard? The first ever encryption standard. And that was, again, I think, built by IBM. The algorithm was part called Lucifer. Lloyd Bank was the first user. And there was a predecessor of the National Institute of Standards and Technology, NIST, called NBS, National Bureau of Standards. They have asked all the vendors that let us know what is the best computer encryption algorithm would be. They asked everyone to submit those algorithms. IBM submitted one, and then they selected that algorithm Lucifer and called it data encryption standard. Although data encryption standard had some flaws in it, so it was corrected back, and there were two gentlemen, Diffie-Hellman. They also created a new algorithm in 1972. So that started being used, and then few years later, RSA came. So RSA was other algorithm for data encryption and security as well. So this is the similar process started by 2016 by National Institute of Standards and Technology. They asked all the industry vendors that submit the new encryption algorithm for quantum safe cryptography. There were 80 algorithms submitted by all the major vendors, you name, like Microsoft, IBM, Google, and others. And they have finalized in 2022 4 algorithms. Those names you see. Have you seen the Star Wars, Star Trek? Are you familiar with those names? Crystal, Kyber, dilithium, some of those things. So I think those are not related, but those are the names for these algorithms. Crystal, Kyber, crystals, dilithium, and Falcon. Those are the 3 algorithms that initially IBM submitted, and they are in top 4. And the person who contributed to Sphinx, which is the 4th algorithm, we also hired him 2 months back. So we can say that all 4 algorithms are part of IBM. But what I'm trying to say here is that this process that started in 2016 with 80 algorithms, they selected final 4. And these are the lattice-based cryptography in general. And the last one is the hash-based, the hash techniques in general. And a couple of months back, or last year itself, they have also asked new mathematical problem, even harder than lattice-based cryptography. So I'll talk about those algorithms as well. So IBM has been helping in building the technologies that can be safe for future. We do already have a quantum computer, not the quantum computer, but quantum safe computer system called Z16, which we have already announced in 2022. So it's a mainframe platform, but still that's the first one that you can see called quantum safe platform. But we have been building these techniques. My role is basically building the quantum safe technologies that you see, quantum safe explorer, remediator, and posture management. I'll share with you more about those. But this is a process, long process over 7 years. They have found these 4 algorithms, which are quantum safe algorithms. And these 4 algorithms are, you see Crystal, Kyber, dilithium, and Sphinx are being finalized, and Falcon will be coming next year. These cryptography schemes, as I mentioned, they are based on lattice, as you see the first 2 of them. Second one is the stateless hash-based cryptography, because they wanted to have another variation to that. The advantage of this is basically the security is solid in the sense, but the performance is not still good based on the data that you exchange, the key length size and the key encryption altogether. So this is one of the part. And the next algorithms that we have submitted, these are the 3 new algorithms they have asked to be submitted, and unique names there: unbalanced oil and vinegar. It's also there are 2 types of schemes. I talked to you about the digital signatures, and the fraudulent authentication, and the other security. We have data in transit as well. So in many of them, there's the key encapsulation, that how do you keep your keys secure, encapsulate those keys. So there's one algorithm in this one is called key encapsulation one. That's the first one. Others are digital signature algorithms. And these are all 3 of them are digital signature algorithms, which are basically securing a particular data or a transaction or data set. And these are based on a unique problem, what we call is multivariate quadratic equations. These are even a little bit more harder problems to solve. When I say that if you have a quadratic equation with 20 variables and 20 expressions, it will be even difficult. And imagine it's more than 100 variables and 100 equations in there. So it would be giving you very, very difficult problems that probably the other ones, lattice-based cryptography, is also not that harder. So this is the next step towards that. And we see the name, as you see, the first, obviously 2 of them are based on these schemes like that. The second one is also important one, what we call short quaternion isogeny signature algorithm. So one of the encryption scheme, which is Diffie-Hellman, is based on elliptical curve cryptography, which is basically, as I mentioned, a curve. But in this case, it's the mapping of already an elliptical curve by another elliptical curve on it. So it's actually a double math problem to be solved in a nutshell. So that's one of the other cryptography scheme that's being suggested. They are not yet finalized, but these are in the race, and we see that one of them will be final soon. So I talked to you about why we are talking about quantum safe cryptography. Hope you understand that, and what is quantum safe cryptography. Any questions here from the room? Okay. Let me talk to you about, I think there are many who should be worried about this problem more. So we know that whoever is protecting the consumers' data, citizens' data, financial data, all of those industries are at risk, right? Banks, governments, right? Telecommunications, our networks are supposed to be secure. Healthcare, our healthcare data as such as well. And then the folks who are basically responsible for the security for these organizations. So those are the people who should be worried about. Many people ask the question, when these quantum computers be ready to crack the encryption? Do we know the date, right? The answer to that is IBM has published the quantum computing roadmap. It's available on the website, which you can find out that when the qubits are coming, how many qubits are available in quantum computers, what caliber of those qubits can be possible, what can they do, what they cannot do. We have, I'm not giving you the details, but there's a possibility that we will have by 2029, 100 by 100 gates quantum computer that will be having error-corrected qubits that can solve the prime factor problem. So that's the part that we should be aware of. So this by end of this decade, it's potential time. And this is what I think we also see from many other organizations. So the National Center of Cybersecurity Excellence, we work with that team closely. They are also speculating that time frame somewhere in 2030. And there's a Professor Mosca at University of Waterloo who is leading the Open Quantum Safe initiative with us. He also predicted somewhere in that time frame when he did it a couple of years back that this is within the 10 years window. So we know that this is the time we have to start prepare for now, because many times the transition to the newer cryptography takes longer time. So it's not like the next day I change it and it's fixed. there are lots of things we have to change in our systems and applications and our network in the enterprise space. Some of the things are happening in the US faster, and there are more mandates than any other country, as we know. So in United States, obviously, we do have this agency we call NIST, but also they have mandates from central government to all the federal agencies, like imagine all the government of India agencies, where they are asked to make sure that their systems have the quantum safe cryptography implemented starting soon. And they have to generate an inventory of those cryptography artifacts. So that's basically they have been already doing. And there's the National Security Agency has also put this timeline. You can see the things in red, yellow, and those things in general. They are saying that you must be having your systems, networking systems, your software and other things should be ready by 2030 to be post-quantum cryptography or quantum safe cryptography compliant. Not only in US, we are seeing this trend across the globe as well. So you see that every country has some initiative using these NIST-based standards that I just talked to you about. And then they are publishing the guidelines that when should you use, how should you use these algorithms, and which industries should apply these. I'll talk to you about the part of how we do it and how we help. I will not belabor the point on IBM part, but there are two things that we have to do in this case. When you talk to a bank and say, this is a threat, what you are doing about it, you have to help them understand the risk. So that's the strategy part. And then you have to use some tools and technologies to find the things where the cryptography is, how to change it to the newer cryptography. So those are the things that we have to build together. So there's this aspect of strategy as well as the technology. The combination of that is one of the programs we help. So once, if I say, how do you get started on this journey to quantum safe? What should I do if I'm a bank, if I'm a government agency, if I'm a telecommunication company? What should I do to be quantum safe? First thing, I think everyone has to understand where's the cryptography hidden in their application, network, and systems. You have to find those. So you have to discover those. Discovery is the first process that you need to understand where the cryptography is hidden in your applications. Once you have that, you have to observe and analyze that cryptography, what we call cryptography inventory, to understand not that everything you have to fix, because as I said, there may be applications in the banks that are customer sensitive data being exchanged or financial secure data needs to be exchanged. So you have to focus on those applications which need to be secured first. So you have to put a priority based on your industry compliance requirements, because it could be possible that you are in healthcare and there are specific compliance requirements like HIPAA compliance, right? If you are doing a business in Europe, you have to find what business applications are required to be safe for your business and your company. And you can definitely look for those crown jewels where they are hidden and prioritize them. Once you have them, then you think of transforming. Transforming part is basically implementing the post-quantum cryptography or quantum safe cryptography algorithms that we talked about, using them, replacing the old ones, and then bringing them together to ensure that your applications, network, and your data is secure. So that's the part of the transformation. There are lots of things I could talk about, but these are I didn't want to talk, this is not the talk about the product or anything, but these are the three products you see around Discover, Observe, and Transform, called Explorer, the Quantum Safe Posture Management, and Remediator. So my team builds these, and I lead this team who builds all three of these technologies. And this is just an example. So when I say this tool basically helps you in your business applications, finding out which place, what crypto method, what crypto function, what crypto library has been used. And you can pinpoint at line level. And it can also identify what vulnerability is there and what is the security risk by using that particular code that you have written in your application. So it can identify all those details for you. and then we put them in a single format, in industry standard format, what we call cryptography bill of material. It's called CBOM. Some of us we know who use software in software supply chain called SBOM, software bill of material, which is basically finding software dependencies, what version of software you bought, whom did you buy this from, all those kind of things. So this is similar to that. And it's a standard that's coming out of what we call a company called Cyclone DX, which publishes these standards. So CBOM is part of that. So this software also builds CBOM for you. So once you have written your application, it can find and give you the cryptography bill of material for that. The second part is the other part. So some organizations who are CISOs in their organizations, they would like to know, how do I understand that within my network where the cryptography is? Because there are applications that you have not written. You got them from like Microsoft, Oracle, or SAP, other vendors, and you don't have source code access to those applications. What you need to do is where those applications are running on a network virtual machine or a server or a device, you can see what's happening through those applications through the network. So you can see the network traffic and you can observe that, and you can find what network handshakes are happening, what cryptography handshakes are happening, and you can analyze that and you can find which cryptography is being utilized. So that's one part. And then this remediator has multiple tools. So you can also test the kind of things that before you implement the quantum safe algorithms, you want to see that if they are giving you the right performance that you have today with the current cryptography algorithms. So you can compare them, contrast them, and even select and verify if that will make sense for your business or not. There are other techniques as well. Some customers say when we talk to them and they say, I have a COBOL application written 35 years ago. The person who wrote the application is retired. I don't even know how to change that application. Is there a way to fix this? So this is one of the approach that what we do is we put a proxy in front of that application, and that is quantum safe proxy. So it actually does all the magic in between. So to the outside world, it's everything quantum safe connection, but behind the scene, it's actually those connections are, you can still keep them working as you have today's cryptography. One of the things, if you remember in my wheel chart, there was a word in the middle of that chart called crypto agility. And I just wanted to share with you what is crypto agility in a nutshell is. So this is, the agility part is different for different people, but I think it's very important for us to know that how effectively and faster an organization can make this switch to quantum safe cryptography in this case. So they can update the cryptography when it's broken or change it when there's a new regulation come from the regulatory bodies, or they can monitor how it's being used and then also obviously retire once it's out of state. But these things require a proper discipline and what we call a crypto agility framework. And you see the right side of the things. You must have an architecture that how you build your applications. You have these things, the implementations of cryptography are modular and abstracted. What we mean by that is don't hard code the cryptography schemes and usage within the application. Rather, you create a centralized service, and whenever you need a new encryption algorithm, you call from the application, give me a new algorithm, give me a new key, give me a new certificate. That's how you will be able to better manage, because you remember that while we are having 4 algorithms are certified this year, who knows, 5 years down the road, there will be 5 new will be coming, and you might have to change them again. You don't want to rip and replace your entire application again. Rather, you build in such a way so it's modular enough, and you can change at one place and the other changes at the other applications, you can fix them. So that's one part. Obviously, in the network side, it is very important because you must have some ways automated. So these kind of implementations, there is a thing that is called Trusted Layer Security Protocol, TLS protocol, which protects all of our transactions that we have. The transactions I named earlier, the mobile banking, the digital card transactions, they go through this called TLS. So their TLS version 1.2 is very predominant, which is not quantum safe. We would like to have a TLS version 1.3 using the cryptography algorithms we talked about. And that would be basically making it safe. However, we have to have that dynamic configuration and management in your network so you can quickly change the TLS versions when you need them. And then obviously governance part should be there, that you are monitoring your cryptography landscape effectively. And then also the standards that you must have in place so that you are using the standards we have built for cryptography, and you have a way and process in your organization that you can effectively change them whenever needed. If you don't have these things in place, you will be repeating that same thing if it's needed 5 years down the road. So that's the important part we have to understand. One of the other things that we know that in these kind of things, it is very difficult for us to win these kind of rallying a particular industry, rallying a set of business altogether. It has to be, I think, team sport concept. And that's the reason we have some of these consortium being built. So one of the ones that I already mentioned, the government and cross-industry consortiums, we have been working like National Institute of Standards and Technologies, that's part of US government. NCCOE is part of US government as well. The Linux Foundation has that we have established called Post-Quantum Cryptography Alliance that has many other technology vendors, you name like IBM, Google, Micron, and some other companies as well. Those, and then MITRE is a standards body, helps support these implementation as well. But then also for telecommunications industries, we have worked with the GSMA, that's the Global Organization for Mobile Technologies and networks. So there's a set of companies like Vodafone, AT&T, more Verizon. Those kind of organizations are part of this, and they have developed a team that is called Post-Quantum Telco Network Task Force Team. And they define these policies and guidelines that how can you make sure that all the telecommunication networks are quantum safe. So those are the guidelines. But also in financial services like banks, the payments networks that are there. So the Emerging Payments Association, the EPA in Asia, also has this Quantum Safe Task Force, QST. Also, this North American ACH transactions. So, you know, every time we do mobile banking, we transfer some funds from our accounts to other accounts. The transaction go through this, what we call ACH transactions. They go every 24 hours in the background. And those transactions are also secured through cryptography as well. So that's the part, the North Americans ACH organization is also building a task force around this so that they can guide all their industry members that which should be the right algorithms, but at the same time, which should be the right techniques to implement the quantum safe cryptography. We do have the roadmap, that our roadmap is not based on the when do I want to bring my technology out, but it's based on how the industries are moving, right? So if government says, I would like to have this particular organization to be quantum safe by this time, so we need to make sure we support those organizations with our technology by that time. So you see all of the regulatory milestones that when the government bodies are making mandates. Second one is that we have also consortia as our bill that I talked about, the GSMA and others. So those are the type of the consortiums that we can build and help organizations. And then obviously IBM has technology that my technologies are in these color-coded swim lanes. And then we already talked about the algorithms that IBM has built them. We have our technology infrastructure as well, as you see in the bottom, which are, some of them are already quantum safe. And we are working on the others as well, because IBM has 6,700 software products. IBM CIO team uses 3,000 different applications, and they are using these color-coded products as well now to make them quantum safe as well. This is my last slide, so I just wanted to share that how do we really build the quantum resilient future with the agility? We talked about the crypto agility concept. We talked about the quantum safe cryptography. Those are the ones. But the first thing that everybody has to do is understand the cryptography. So the visibility is very important, right? The discovery part, I told you. So discover your cryptography first that you have in your business. And then obviously prioritize them, which is the observe part we talked about, that finding out where your crown jewels are, what your business impact is. And then you prepare for the quantum safe transformation journey. And then make sure that you comply with your regulatory requirements, because not everything required to be quantum safe. So you have to pick and select those things. And then make sure your applications, your network infrastructure and systems are built in such a way that we can make sure those have the agility in there by default. So that's what it was. So I will open it up. There are lots of these slides I can share with Mr. Shah. So these can be made available if you would like to see them later and reference them for any other reasons. So that's all for my talk today. Any questions or comments from you guys?
Pass on the mic first.
Evening, sir. First of all, that was a very interesting talk. Thank you so much. So my question was that India as a country was not so far long ago started getting acquainted with internet and technologies. So how do we think we as a country are equipped with infrastructure, or rather awareness, to deal with the threat of this quantum threats, or how are we equipped to be quantum safe?
Very good question. That's why I'm here. So just to spare the awareness is one part. You are right. We have been working with many organizations as of now. So I would not be speaking their names on this video talk, but they are government central agencies and banks that we have been working in India already, talking to them about this. So they are aware of the threat. But question is how they prepare faster than other organizations. So everyone is sitting and waiting. So it's that part, obviously, but there are few governments, few countries are faster than others. Not that India is sitting idle. If you go to Delhi, probably there are the organizations who already know, government agencies already are aware of this threat, and they are preparing. And mostly, I think government and defense, those are predominant organizations. Banks are already thinking. I have been talking to many banks in India, and they are already preparing for this. So it's not that awareness is not there. They have been waiting to get the NIST final standards, which will be finalized by July this month. And then there will be a lot of traction. So I would say by 2025, you will see lots of projects will be emerging saying that we are doing quantum safe projects or post-quantum cryptography implementation. So that will happen. Yeah.
I have one question. This is from Zoom.
Sure.
Please go ahead. May I? Yeah, go ahead. Yeah. So this is Shrikant from TIFR Bangalore. I want to know this computing infrastructure wise. Let's say 2048 beat to beat that. The computation infrastructure has to be very massive. So that comparison with existing that infrastructure and the infrastructure required for quantum computing, quantum-based cryptography. Can you just give us comparison between that infrastructure?
Right. So if I understand your question, you are asking, let me just rephrase. Hopefully I wasn't clear in my talk. The infrastructure that we have today, by default, none of that is quantum safe. Okay. And in order for us to make that quantum safe, we don't need quantum computers, right? So this technology we have is purely made for classical computers, a new math problem, although it's called quantum safe cryptography or post-quantum cryptography. So it's basically replacing our existing encryption techniques and our cryptography schemes within our current systems. So that's one part. And these schemes that we are talking about will be implemented at You might have in hardware side, you mentioned infrastructure called hardware security modules, HSM systems. Those will be replaced with the quantum safe cryptography based hardware security modules. So that's the immediate solution for those. And then also in the network, I talked about this TLS, the trusted layer security protocols. Those are the ones you have to replace to or upgrade them to TLS 1.3 with implementations of Kyber or the MLKEM algorithm. Does that answer your question?
Yes, thanks.
Thanks. Anybody has any other question for Jay?
Good evening, sir. Sir, so is it going to create much more safer blockchain technology also? Will
Very
it
good
help in
question.
that?
Very good question. So I didn't mention that. I know Mr. Shah mentioned about one of the things that I wrote a book on blockchain for business. So that's one of the other good part that you reminded me. So yeah, I know. I think that's the one of the things. So I don't know how many of you know about the blockchain. In blockchain, by just the word of what blockchain is in itself for the rest of the other guys, the reason it's called blockchain is that every time a new transaction happens in the system, a block of information is put on the system. Anything changed to that transaction, a new block of information comes and attached to the same. And there's a chain of those blocks. But one important thing is every block is encrypted. Every block of the information is encrypted in the system. That's why they say this is the most trusted system or platform. The reason we don't have a lot of blockchain implementations because nobody wants the trust and transparency in the organizations, especially governments, right? Everybody wants to be corrupt and be corrupt. So that's the one of the things we haven't seen much of the implementations there. So obviously your question is very right. So blockchain where, every transaction is encrypted, it will absolutely make those transactions secure. But it's needed. It's a need, not necessarily it will make them more secure because whatever they are using today will be requiring to be using this quantum safe cryptography. So in the trust protocols that we have today in blockchain, all of them use our existing technology and those need to be upgraded to quantum safe.
Okay, sir. Thank you.
Yes.
Questions, please? I have a very quick question for you. You are already department of your IBM Quantum is actually making quantum computers.
Yes.
So do you have a litmus test sort of thing that you have your algorithm, you go then check with those guys that, okay, see how many years you will get to crack this ones? On a practical level, how do you justify that? Okay, you may say, okay, for the next 20 years, quantum computers may not progress to a level, but current standards are being defined, as you said, the July standard.
Right.
So do you have some ideas about how long it may take for a, say, state-of-the-art quantum capacity right now, what IBM has?
Right. So I'm not allowed to give you exactly the date, and I do not want to threaten the people that IBM is saying their quantum computer will come by this date and will break this stuff. So legally, I'm not allowed to say that part, but we are certain that by 2029, we will have error-corrected qubits that could solve potentially the factorization problem. That's what we can say. And our quantum computing roadmap is open and public. It's not something that only we know. However, these testing kind of thing, more than us, NIST will be testing. And they will be the one if they say that these are broken or not, and they have tested. But they have been testing over last 7 years. And they are confident that that's the reason they wanted to make sure we have post-quantum cryptography algorithms, because they are certain that by this end of this decade, there will be quantum computers of enough caliber. And the other part is, while you and I sit in this room and keep talking about who will have it, but there will be a bad actor or nation agency altogether who might be just creating a quantum device, just solving the cryptography problem. Forget about the rest of the quantum computing use cases, but just one use case. Let's solve the cryptography problem, and they will create a quantum device. And once we will know, and we will say, oh, now we are at risk. So I think that's the part.
Thank you.
You are welcome.
There are no more questions, so we'll just join in uploading the Jai for giving us a wonderful talk and overviews of it.
Thank you.